And welcome to the Woven Skies, Science and Art from Air to the Cosmos exhibition that you're enjoying here. And in conjunction with the exhibition, we are doing these lasers. So I'm Andrea Polli. I'm a professor of art and computer science at UNM, and I'm also a member of SciArt Santa Fe. We promote excellent in art science at that intersection we call SciArt. We've existed as a nonprofit since 2019, and one of the things that we do is these lasers. And lasers are, it's an acronym for Leonardo Art Science Evening Rendezvous. They were started by the Leonardo Society for Art, Science, and Technology in San Francisco, probably about 25 years ago now. And there are lasers that happen around the world in about 50 different cities. So we're very proud to be the host for lasers in New Mexico. I want to thank Santa Fe Art Institute for this wonderful space, for us to have our exhibition and our events, and our donors, including individual donors like you. We really need this. We, like many nonprofit organizations, we had a grant terminated just a week and a half ago. So we're really, and all these, I mean, every NEA was terminated. So if you are enjoying organizations like us and other organizations, be sure to donate to them because everybody's having a hard time right now. You can subscribe to our upcoming programs, our monthly newsletter at sciartsantafe.org. This is our big month, so we're having this exhibition, which will close on May 25th, and every Saturday and Sunday we have events happening. So next Saturday we have another laser on mystery and intuition with Maryam Hojati, who's here, and this work here, and Shirley Crow and Joan Stango. On May 18th, we have another laser called Flux and Feedback with Kristen Angerbauer, who's this incredible work here, and also Zuiva Sevilla, who's the infrared piece there at the light boxes in the entryway. We're having a special event on May 23rd at the Chaco Visitor Center. So a half an hour before sunset at the Chaco Visitor Center, we're hosting Agnes Chavez and Julia Bluebird to give a presentation. This is also a star party. So all these amazing astronomers and astronomer enthusiasts bring their incredible telescopes, and you can hang out and check that out. And if you're interested in that, just pop me an email, let me know, and I can give you more details about that. Then on May 24th, we're going to have an artist salon.
Would you say that again, please?
Artist salon. So we're hoping all the artists, and many artists are here. This is Susan Latham. There's a wonderful red piece there, sculptor, animal sculptor. So you'll hopefully be here at the salon at 4 to 6 on May 24th, along with Alice Santoro, who's also here, and other artists that I mentioned. And then on May 25th, there'll be our closing event and a laser also with Agnes Chavez and Julia Bluebird. Coming here May 25th. So not only in Chaco, but you'll be able to see her here. No, you'll have to organize that yourself, but we do have some, I can give you information about stuff. Okay, so our talk today is materials and sustainability on Earth and beyond, with myself and my colleague at UNM, materials engineer Maryam Hojati. So without any further delay. Thanks,
Good afternoon, everyone. Could you hear me well? I could hear myself. So my name is Maryam Hojati. I'm assistant professor at the University of New Mexico. I did my master, PhD, and postdoc at Penn State University, and I started my new journey as a professor at the University of New Mexico in 2019, right before COVID starts. I established and led advanced sustainable construction lab at the beginning of starting at UNM. And in this lab, ASC lab, I'm working with a team of undergraduate and graduate students on different research about sustainable construction materials. And you can see a list of my undergraduate and graduate students. Some of them graduated over the last few years for their PhD or master degree and undergraduate degree. And currently I'm working with 6 more students, 3 PhD, 3 master students on different aspects of, good to know. On different aspects of sustainable construction in terms of material and practices. So, Advanced Sustainable Construction Lab, or ASC Lab, that I established at UNM has 3 different areas of research. We firstly try to develop innovative and sustainable construction material with some carbon cautious approach. We try to adapt the new technology like 3D printing to be able to have some more advanced construction in terms of speed and cost. And we are also trying to capture carbon dioxide from environment and store it in the construction unit. So this is another round of research that my team are working, and in the next few slides, I quickly just review some of the research that ASC labs are doing currently at UNM, and then I'm gonna just have a review of the big picture of doing 3D printing in construction for Earth and beyond the Earth. So in our lab, we were able to design some 3D printable self-reinforced material. This material is very similar to concrete, but it's bendable, so similar to metal. If you bend it, as you can see in the video here, see? My assumption is that you can see everything.
Try putting it in again.
There we go.
It shows, so maybe you're saying this. Okay. So this is the bendable concrete that I mentioned. It's similar to concrete, but if you bend the concrete, it easily cracks, right? This material, similar to metal, it could bend. This is the material that we patented. It's self-reinforced material. We could embed it in the construction without the need of the reinforcement or external reinforcement like rebars, steel rebars that we have currently in the construction industry. Another round of the research is about using local material like pumice. You know, New Mexico is rich in pumice. So we adapt this material for 3D printing application, and we achieve great property, especially because the pumice aggregate is very light and porous. So we use it as an internal curing agent. In the arid area, the concrete needs to be cured. When it's exposed to dry environment, it could not be cured fully. And by using this internal curing agent that could hold water inside the concrete, it could achieve very high quality of strength over time. Another area of the research that we did, we used biopolymers, different sort of starch. Xanthium gum was used in the concrete as a rheology modifier material for 3D printing to make the material printable. So currently, most of the 3D printing industry are using some polymer-based material, which is coming from oil industry. By use of this bio-inspired material, we can minimize the use to those materials. And one of the interesting research that I'm very proud of is using local source material like mud or dirt in New Mexico to be adapted for construction industry of adobe hubs. So as you can see, New Mexico is one of the major states for using local soil for so many years as a construction material, and we collected material from different parts of New Mexico. We characterized this material with material tests, and we ranked them in terms of their printability. As you can see, some of the 3D printed parts that we have here, it's all made of pure soil from New Mexico. We try to engineer some of the property of this material to address the printability issue that we might face it during the printing. You can see some of the printed part with local soil material. Additionally, again, we use pumice as local source material for 3D printing application. We study the experimental computational analysis of fracture behavior of this 3D printed material. So because printed material is all about layered material, it's completely different with the bulk material in terms of mechanical performance, and because of that, we try to characterize and computationally simulate this material to make sure in terms of mechanical performance we can achieve similar comparable with concrete or other construction materials. Cement-free material that is called geopolymer is another part of my research. This material is very, very similar to normal traditional concrete which is used in the construction, but because cement is not sustainable material, we try to minimize its application and use in the construction. This is the material which is cement-free and very, very similar to the concrete that we have. We try to adapt it for different construction purposes. One of them was with the use of hemp. So we mix hemp and geopolymer. We make some material which is structurally sound and load-bearing. On the other side, it has high insulation property because we are using hemp material. We additionally use polymer material when it comes to construction for lunar application. Another part of the research that we are using, we use the lunar regolith or native lunar soil. We try to adapt it for construction and making some construction material with those lunar regoliths. Currently we have some NASA project going on with Artemis team to bring some of the material from moon, and this is the part of the research that we are doing, and geopolymer would be the only option that we have to make construction material for lunar purposes. We have some asteroid project. We are working on mechanical property of asteroids, so we try to make some asteroid material in the labs, and then we characterize its mechanical property. This is another NASA project that currently I'm doing at UNM. Another project which is very interesting is about how we can jointlessly connect a structural material like geopolymer that I showed in the previous slide to transparent material like glass. This joint is very strong and prevent any energy loss from the joint. So this is another project that I started. It's functionally graded material where we need it to be transparent. We have the glass, and when we need the load-bearing material, we have the geopolymer, as you can see in this slide. And the other part of the research that I'm currently doing is about how we can capture the carbon dioxide and store it in the construction material. So this is another research that we developed some calcium carbonate material from calcium waste, and we try to use it in different applications for construction industry. This picture is me about 6 years ago in May 2019 at the last phase of NASA Centennial Challenge in Peoria, Illinois. I'm going to review some of the material about this project, which is very cool and exciting at the last part of my presentation. But for now, I'm going to just review what one of the most challenging problem in the construction industry and how we can address it through the research that we currently do at UNM. So we have about 1 billion people currently in the world who are suffering for living in substandard condition. And over next 30 years, there would be another 2.5 billion who are gradually migrating to urban area. And with this rapid urbanization, with the climate change and shortage of resources and material, the need for affordable and dignified housing is just going up. However, the demand is high, the supply is very low, especially in the United States, as you are all aware of that. Let's see if construction industry has the capacity to address this high need for affordable construction. So construction industry is one of the biggest industries in the world economy. It worth about $10 billion per year. And it has been suffering for so many years because of low productivity. While other industries like manufacturing industry or agriculture change the way that they are making their products and goods over the last 100 years to be 10 to 15 times larger, construction industry remain in the same productivity over these years. And however, we saw in the previous slide, the need for affordable housing is urgent, especially for large amount of population who are gradually migrating into urban area. And it's the big problem in the construction and the industry over the last 100 years. And when the COVID started a few years ago, one of the industry, the big problem was construction, because social distancing doesn't mean anything. Most of the work is very labor intensive, it's done by human, and it's hard to bring automation or social distancing to this type of industry. So let's review some of the problems that we have in the conventional construction. The traditional construction is very slow, when you want to construct a house. Sometimes it takes very long, close to a year, to finish all process that you need to do for construction. It's very labor intensive. It's, as I mentioned, it's majorly done by human, right? It's very manually performed. It's one of the dangerous jobs in this country. In average, about 10,000 people killed during the construction process each year, and 400,000 are injured during the construction process, which is a large number of people working manually in high, dangerous, and non-safe atmosphere. Because there are so many trades involved in the construction industry, is highly prone to corruption. This is another problem in the construction industry, and it's always over budget. Budget and cost is one of the major issues that, as I mentioned, we need to think about affordable places. And this slide shows one of the McKinsey report in 2017 when they compare the productivity in 3 different areas: in construction industry, in total economy, and also in the manufacturing industry over 20 years. And as you can see, for construction industry, the one in the orange color or red color, there is just 20% increase in the way that they are producing, while other industry or manufacturing, they double the way that they are manufacturing goods and products over all of these years. So this is one of the major problems that construction industry is facing, and especially this problem is going to be bigger and bigger with years because the number of people who need affordable housing is increasing. But let's see how construction industry could address this problem. So this slide needs to be, So the human tried to address the low productivity issue over the last 300 years through different industrial revolution. So anytime that human tried to find a solution that could make a cheaper products for larger or broader number of people and bring quality to the life of so many people, they call it industrial revolution. The very first industrial revolution was the steam, when the steam came into play. The second one was electrical and assembly lines. The third industrial revolution was the computer and also the automation, that it was started about 50 years ago. And currently we are living in the fourth industrial revolution, what is called Industry 4. And it's all about the smart factories, where all of the systems are connected, are augmented with web connectivity, and they are connected to a center system that could visualize all of the production chain and make its own decision. So this is what we call it cyber physical system or Internet of Things that you might hear about the new era of industrial revolution. And there are some rumors that we are about to change the industrial revolution to the fifth one by the new advancement that we have in terms of AI, machine learning, and everything. But all of this industrial revolution changed and transformed the economy, which was based on agriculture and handicraft, to the new industry, which is majorly based on the big factories or systems who are majorly could achieve larger products and goods. So by considering all of this digital revolution, if construction industry try to adapt some of them, they could address the low productivity issue, to majorly address the slow production, to have faster construction, to address the cost, and also address the low quality of the work. And 3D printing is one of the outcomes of third industrial revolution and has high potential to change the way that we are constructing nowadays in the construction industry. So 3D printing is all about how we can make any three-dimensional object with a digital file. And it has been growing in terms of popularity in different industry, including food industry, aerospace, bio printing industry. And in the next slide, I'm going to very quickly review some of the advancement in different industries in terms of the adoption of 3D printing. But before that, this slide shows the general concept behind 3D printing. So for any dimension, any three-dimensional object that we want to 3D print, there are some examples here. The first step is making a three-dimensional digital file in CAD. Then, because we talk about layer-wise deposition of the material, we need to slice them in the proper way. And finally, the digital file should be translated for the robotic arm or mechanical system. And finally, we are able to 3D print the final shape that we are interested in. And there are some examples here, as you can see here. So I'm going to quickly review some of the application of 3D printing. One of the major application in bioprinting. So 30 years ago, when 3D printing was started to grow, bioprinting was one of the major industry that adapted and tried to 3D print different parts of organ or body parts by use of this new technology. They used some sort of living cells to 3D print and from different parts of the body. Dentists are also embracing 3D printed goods in rapid way. So some of the dentists currently, if you go to their office, they have a small printer, and in very fast way, they make all of the required pieces that the customer needs. Artists are also enjoying the use of this new technology. So in very fine size or large size, they can adapt the new technology to make any piece of art. And what you see in this slide is all 3D printed part of the artist by use of different materials. This is a very first car that was fully 3D printed 10 years ago. And currently there are more advancement in auto industry, and the imagination is that someday we could just work on the 3D printed house that we dream always about and send it to the local printer in our house front to be printed and ready for our application. Some of the fancy restaurants also start using that to make different forms of noodles. There are some of them in California that I recently visited that they use this new technology to attract more customers. If you have a sweet tooth, maybe chocolate is another thing that the chocolate makers try to make different forms of chocolate by use of 3D printing. So previously they tried to cast all of this material into molds, make different shape, but by use of this new technology, there is no limitation in terms of the shape or geometry. They could make and 3D print anything. And the last thing is about the NASA competition. About 10 years ago, they invested $125,000 for a project to 3D print pizza in space, and the result is shown also here. So there are so many great adaptations in the use of 3D printing nowadays in different industries. How about for house construction? Do you think is it feasible to be used for constructing house? Yes, of course. There are so many great work, especially over the last 6 years. There is like day-to-day change in adaptation of the industry to use 3D printing to have 3D printed homes and houses. But and because of all of the problems that I mentioned earlier, definitely construction industry has high potential to adapt this new technology. It could reduce the construction costs, it could fabricate any geometry from simple to intricate because of we are adapting all of the automation into the system to 3D printing anything. It could reduce the amount of energy, time, and material that we waste during the construction process. But there are big hesitations when it comes to the 3D printing, and it all returns back to the scale. When we talk about the 3D printing of a house, it's completely different than 3D printing of bio parts like body part or organ. So a scale is number one problem, and it addresses so many other things in equipment parts. That's the size of houses are really big. It's hard to have large 3D printer to 3D print the full house. The involvement of different trades, as I mentioned earlier, so there are so many trades with good enough resistance to any effective change. So just convincing everyone that you're gonna pay more is another problem. Lack of trained and technical workforce, this is the thing that at university we try to address it by training new engineers who are ready to use new technology for construction. We need to design new material. Definitely traditional, conventional material could not be used in 3D printing application. We need to work on the material side, how to reinforce the material to make sure it is structurally sound and viable. This is another thing that we need to address it. Up to now, the application of 3D printing in the construction is limited to whatever we listed here. First of all, for emergency housing, for those who are the victim of any man-made or natural disaster, so they don't need to spend like long time without any shelter. This new 3D printing technique could give them some shelter or temporary shelter in a day or so, because it's very fast. For low-income housing, we could have some affordable housing for the 1 billion people that I mentioned in the first slide. Whenever we are considering environmental aspect, this would be one option because the amount of waste which is generated during the 3D printing process is much lower. For functionally graded material, one example was shown before that we have glass to geopolymer jointless connection. This is another way that we can automate the system to have different types of material with different functionalities sit together and form the building. And the last but not least is the space colonies where there is no labor or it's hard to do construction. So we train the robots to do all of the required construction for us. So one of the materials that currently is used for 3D printing application is concrete. Concrete is made of cement, gravel, and sand, and water. This is not really environmentally friendly material. It has been using large amount of cement, which is not green material. And other material that we really love it is natural material like soil. We have so many great material in New Mexico, native material in New Mexico that has been used for so many years in the construction, and it has high potential to be used in 3D printing. So this is the list of some of the 3D printing companies that currently are working around the world on larger scale construction of houses. Some of them are US-based, like Apple or Icon are doing great. I don't know if you heard about Icon in Texas, Austin. They are printing the full neighborhood by use of the larger scale 3D printing. This is one example of 3D printing 2-story houses. in Belgium, and they started this project, I guess, 3 years ago, and they finished this project just in 2 weeks, 15 days. It's very fast. They said they use 60% lower construction materials. They emit 50% less carbon dioxide, 3 times a stronger material because their material was engineered. They just have one person needed to monitor the entire construction process, and it was designed for 2-story building. We have also some other example. This is one of the center in Dubai, that the food center was 3D printed by one of the US-based company, Episcor, and their plan is that by the end of 2030, they're gonna finish the 3D printing of the entire center by use of the new technology. In France, there is a neighborhood that they try to 3D print for low-income and homeless people by use of this new technology, and with the idea that it ends in lower cost and more affordable case. And in the US, as I mentioned, ICON also makes 60 family affordable houses in Mexico. So ICON is a US-based company, but they did it in Mexico, and currently in the Austin, they are 3D printing a complete neighborhood for that. So other than 3D printing of houses, there are also some applications for infrastructure, like the wind turbine tower. So previously, the wind turbine tower was up to 100 meter height, but by use of new technology, we can achieve to higher height, like 200 meter height, and achieve larger energy, wind current, and generate more energy from the wind turbine. And this is one of the examples, again in Europe, they try to simulate the 3D printing of one of those wind turbine in the lab. So as I mentioned, the last item that I have here is all about the application of 3D printing for colonizing a space. And this is the last part of my presentation, that I'm going to review one of the NASA projects that I did during my PhD and postdoc at Penn State University a few years ago. So space colonization have been argued for so many years. There are so many arguments against and in favor of space colonization. Those who are supporting space colonization, they have 2 major causes. One of them would be survival of human race because of some man-made or natural disaster that might happen, who knows, and availability of more material and resources when it comes to the space. Professor Hopkins predicted that the human race, the way that we are living nowadays, would become extinct within the next 1,000 years. Yes, 1,000 is a lot, but it would happen if we're going to consume all of the natural resources that we currently have on the Earth. And he predicted that humans have just 2 options. One is to face the prospect of long-term extinction, or by colonizing the space within the next 200 years, we are able to have some other option if something happened to our lovely house or Earth. So, because the resource in terms of material and energy is endless, is enormous in space, NASA administration identified the space colonization as the ultimate goal for most of the current spaceflight programs nowadays. So the solar system by itself, which is shown here, has enough material and energy to support anywhere between 1,000 to 1,000,000 times larger what we have currently on Earth. So all of the options that we have in the inner planet, the asteroid belt, and other planets could be considered for a space colonization. And this slide shows some of the options that NASA is currently studying. The very first one is the near-Earth space or moon. So there are so many researches going on about how we can colonize moon or start having some lunar habitat on moon. The second one is inner planets. There are so many teams researching on Mercury, Venus, and Mars. And and we know most of the research is majorly focused on Mars, and we have great success. NASA had a great success up to now about finding more information about Mars. Asteroid belt is another option, and moons of the outer planets like Saturn has also high potential to be used for colonizing space. But in the last few years, NASA, not last few years, about 10 years ago, NASA designed and partner designed a $2.5 million competition to build a 3D printed habitat for deep space exploration. They invited the industry and academia to come together with any level of innovation to see how we can push the boundaries for 3D printing of houses out of the Earth planet. And this is the start of my story when we, with a team of the engineer at Penn State, we formed a team and we started working in this multi-year project. It took like 5 years from phase 1 to phase 3 to finish this project. And the major goal was to push all of the boundaries for the application of 3D printing for Earth project and then for a space project. Because at the time, it was 2015, and there were just limited numbers of projects going on 3D printing. So I worked with this team of faculties and a student. I did my PhD and postdoc with this team and work on different aspects of NASA Centennial Challenge from step phase 1 to design the material all the way to phase 3 that will be 3D printed low scale or small scale habitat. So we formed a team, an interdisciplinary team of material students, a system design team, and some team from Department of Architecture that came together to work on 3 different aspects of material, system, and design. They are all about the relationship between these 3 aspects that we study in our study. So the thing that I started this research was about which material. So when it comes to the construction on Mars, definitely our goal is not to transport material from Earth to Mars. This is the goal, to use the local resources or indigenous resources on the space. And because of that, my goal was to find some material that could be used for Mars construction. So I started with 3D printing of the local material on Earth, or cement. So we designed some material which was printable with local cement, and then we tried to study what is available on Mars that we could adapt it for construction industry. So the first thing that we need to make concrete is aggregate. It could be sand or gravel. We studied that Martian crust consists of volcanic basaltic rock. So over the dust, if we remove the dust on the Mars surface, we can have these 30 to 100 kilometer basalt, which is similar to the basalt that we have on Earth. So this is good, but because there is no calcium-bearing compounds on the surface of Mars, it's not possible to make cement. We try to study which other material is available, and we noticed that kaolinite or kaolin is a type of clay which is used in ceramic application on Earth, is available on a specific location on Mars. So if we can use this material, calcine it, we could achieve some material which is similar to cement, and we could activate it to make adhesive or adhesion property to be used for construction. We assume that we are allowed to use the water, the low amount of water that they found on Mars surface. This was our assumption, but I don't know in future if they're gonna find more, or there would be some other options to make water from hydrogen and oxygen on the on the Mars condition. And finally, by combining all of the material resources that we find on the Mars surface, we were able to design geopolymer-based concrete from indigenous Martian material. We call this material Marscrete. So this is me 10 years ago. I'm very younger than now. And we started in a small lab the team of students and faculties to just do anything in a smaller scale. So as you can see, this is the 3D printing system that we have at the time. We have a small robotic arm. We use a very small blending system. The mixer system was just similar to the mixer that we make dough at home. So we have a small pump, and everything was in very small scale. And the very first phases was all about how we can 3D print a cylinder. And believe me or not, we spent like 6 months in the lab, day and night, to be able to achieve this stage, which is very simple nowadays. So at the time, there was no references. We were very first team who started this type of project. It was hard to make the material stable and buildable enough. After printing few first layer, the material started flowing down. And it was one of the problems. After 6 months of working on our material and experimenting different things, we were able to achieve 3D printable Mars-grade material, and we passed the first few phases of the NASA project. And then for the next phase, we increased the size or scale of our printing system. In a head-to-head competition, we were able to 3D print a bigger dome by use of the low amount of supports, and we achieved all of the requirements by NASA. We won the second place in this phase 2 of NASA competition. In phase 3, there were multiple levels. In the first level, they asked us to 3D print a foundation and study the mechanical property, the quality of the print. We 3D printed also some system, some water component system, and study the leakage from the system. And we, in all of these phases, because we meet all of the requirements, we win some awards. We have also some virtual competition to design a 1,000 square feet of living space for astronauts. Do we have time to show the videos for this virtual?
I don't know how long.
It would maybe work.
Oh, yeah.
So this is.
Colonizing space is the next great leap for humankind. Of all the inner planets in the solar system, Mars, the red planet, is most similar to Earth and considered the best option for human colonization. An abundance of materials and energy make it possible to construct a permanent habitat, the first step toward a human settlement, but you need a place to build. Scanning the surface of the planet, one location for our permanent station stood out, the Endurance crater. Conditions on Mars are inhospitable and pose big challenges to human life. Because of the expense and limitations of space travel, we will need to maximize the use of indigenous materials and resources. Our strategy builds on our current research to develop low-cost housing on Earth using parametric BIM design and additive manufacturing. The construction process involves a robotic arm printing a geopolymer concrete mixture called Mars-crete. Mars-crete consists of indigenous minerals, including basalt, which is crushed and used as aggregate. Kaolin has to be calcined to obtain metakaolin, which is used as binder, and sodium and silicon compounds, which are used as agents to activate metakaolin with water, obtained from ice. We understand the hydration reaction with gravity by studying the solidification of concrete aboard the International Space Station. Another key aspect stems from our research on the development of braided composite materials that permit a seamless and impermeable braided transition between opaque and transparent surfaces, such as our engineered geopolymer concrete and boreal glass. The composite material is lightweight, thermally insulative, resistant to chemicals, freezing, and fire, as well as impermeable and protective from cosmic radiation. This technology promises to have significant impacts on building processes, architectural language, and the spatial experience of dwellers. The design concept considers the maximum angle that can be printed without formwork, the minimum wall thickness required to protect from radiation, the maximum reach of a robotic arm, and structural stability. The result is a basic unit formed by a cylinder and a cone. The finite element analysis considered the principal tensile and compressive strength, considering the interior of the building will be pressurized. This conic unit can have varying sizes and be connected and combined in different ways to to obtain different shelter configurations, adjusted to different programmatic requirements and specific site conditions. These principles guarantee expandability as more units are added to the original design. Among multiple possible design options, we chose one to illustrate our concept. Each unit is composed of a protective shell made from indigenous geopolymer concrete and a lighter interior constructed from both indigenous geopolymer and recycled plastics with 2 floors. By manipulating the seamless transition from geopolymer to glass, we can provide 2 types of openings. From above, giving each unit ambience lighting, and from sideways, allowing for views towards the Martian landscape. There are 4 units for work, living, sleeping, and gardening. Entry chambers on each end of the habitat enable access from the exterior and emergency exits. The first unit includes a wet lab, meeting area, and storage on the first floor, and individual workspaces on the second floor. These 2 different workspaces are articulated by a staircase. The second unit hosts the dining area, the kitchen, and bathrooms on the first floor, and a leisure area on the second floor, accessed by a second staircase. The third unit includes the sleeping quarters on the first floor and workout and leisure areas on the second floor. The design was conceived to enable visual communication between the various units and floors, thereby offering a spatially rich living environment. The fourth unit contains life support and hydroponic systems with provisions for emergency situations. Each unit can be sealed and will have life support capability during repairs. The printing system is mounted on a rover. It includes a retractable dome that guarantees proper conditions for printing. Once one module is constructed, the rover moves to print the next module. This strategy will enable the creation and growth of thriving human colonies on Mars. Colonizing space.
So in the next stage, they ask us to 3D print the small scale habitat in the Caterpillar Center that I showed you the picture at the first few slides. So to do that, we have a smaller scale of the habitat that we design in the virtual case, and then the major goal of that stage was to achieving high automation, because there is no human for sure on Mars. So we try to minimize the human intervention during the construction process. Because of that, we increased the size of the printing system that we have. We added few silos that were all automated and bring the material, mix the material, and send them to the nozzle for 3D printing. And we added another robotic arm to place all of the opening after finishing the 3D printing of the layers. So this is a picture of what we achieved during the construction process, and I'm gonna skip these to show, that is a long video, but this video is what is published by NASA in this competition. So it was a head-to-head competition in Peoria, Illinois. About from 67 teams that we had at the beginning, just 2 teams make it to the final. One was Penn State, and the second one was from one of the space factory industry teams. So they use some sort of bio-based material to 3D print their habitat. This is what you can see. And it was the very first time that the construction process was fully automated with minimum human intervention, as our geopolymer material is on the other side is also printed. The habitat was tested for the smoke test, for crush test, and impact test, and finally Penn State win the second award in this NASA Centennial Challenge. All right, so I'm thankful for all of our research supporters from NASA, NSF, from DOT, who help us on different aspects of the research currently at UNM. I'm doing the similar research with my team to make construction possible on lunar surface. If you have any question, I will be happy to address, and you can check our website, ASC Lab, if you scan this barcode.
So I'm gonna go through pretty quickly, I think. So hopefully we have some time to do a little Q&A. There's so I'm just blown away and there's so many questions for Mary and myself. Of course, presenting from the perspective of an artist, working with some of these materials, and I have a little bit of a background about my work. So I've really been working a lot with this, kind of historically over the past 30 years on the idea of air and the movement of air. That's a little nicer. So I've been doing a lot of projects related to air and the atmosphere, loving some of the ideas of David Abrams about air and environment. I started out really in the early 2000s working with weather, and this is a project that I did, sonifying weather data. I went to Antarctica and worked alongside scientists, recording the Antarctic soundscape and also sonifying some of their data. I did an album called Sonic Antarctica and a book called Far Field about that work. I've worked physically with air quite a bit. This is a piece called Breather, where this kind of bouncy breeze over as if you're breathing into a bag. It kind of expands and contracts over a car. Did this project as if you could see the emissions that a car is creating. This is what it would look like, but this is in the form of mist. And I had a mobile version of that using compressed air and water, and also projecting onto the mist different types of stories. And then in early 2000, I worked with a group that after 9/11 was thinking about what Earth would be like in 2050. And I came up with this project to light the necklace lights on the Queensboro Bridge. I was living in New York at the time, near this bridge, and they actually turned the necklace lights off after 9/11 to save energy power. And so I came up with this conceptual idea to use wind power to power the lights on the bridge. And one of the things I learned was that a weather station on top of the bridge would be a form of an engineering feasibility study. And so I started to get these weather stations, and then so I worked with weather stations a lot, and then I found out about air quality monitoring, and I worked with a number of different air quality monitoring stations to create this piece and a number of other pieces that show real-time air quality. So this is called Particle Falls, but I'm going to fly through a lot of this stuff. This is a piece at the Anderson Crusoe Balloon Museum in Albuquerque. That's currently on view, has been since 2014, that shows wind speeds. Red if you can't launch the balloon. And what's been really nice with that, working with these LEDs, is that they're really scalable. So in 2016, I had the opportunity to do a wind-powered light installation on a bridge in the Rachel Carson Bridge in Pittsburgh. So it's kind of a nice full circle for my work, because I was able to take this conceptual idea 15 years earlier and turn it into something that even went beyond the original idea, because it created these animations. So I now have a permanent piece in Pittsburgh called Garrison Canal that shows precipitation and temperature, and then this permanent piece in Tampa, which responds to people's movement under a bridge between the Marriott and the convention center, kind of inspired by bioluminescent bacteria. But this is what I really want to get to, which is kind of my new work with thinking about materials, which is why I really wanted to get to know more about Maryam's work, which is so incredible. And so I started to work with embedding air in materials and created, really looking into engineering, material science for foam glass, using waste glass to create insulation. And I developed a way to create art glass with that is foam. And I just want to kind of share these things because they're so nice to touch because they're so light. They are fragile like glass, but they're really lightweight and kind of interesting to work with. So I embed the glass powder with calcium carbonate and other minerals to create these kind of foaming and, to me, visual representations of air and the foaming that happens in the kiln or happens in the hot shop, which is this piece here. And I've been experimenting with other ways that bubbles are embedded in glass, super fascinating. And at the same time, in a kind of a parallel investigation, I've been looking at sound, and I have kind of a long background in sound, looking at how sound might create a shape. So that's something of what you see here. So this is a sound spectrogram. Here's a couple of different ones of soundscape recordings that I took. I think this is a bells or a bird sound. And then what I've been doing over the past year and a half or so is, let me turn this down, has been mapping, working with a really good animator, much better than my digital skills, Nuno Souza. And we've been mapping these spectrograms on three-dimensional shapes and trying to create these forms that represent sounds. And so, and in this case, the sound is like a dough, and I made bread bowls out of ceramic and baked bread in the bowls. And just maybe quickly to show, so this is an example of a 3D printed version of one of these map spectrograms. And when you see these sort of sharp edges here, there's sound harmonics. So when you have a bell, you have a number of different sound harmonics that happen. So it's not scientific at all, but the idea is that, perhaps you could touch and feel a sound if you were hearing impaired, and you could get an idea of what that sound might be, or just by looking at it, you might get an idea of what that sound is. So then I've had the pleasure, I've been teaching bioart design for a long time, and have had the pleasure of working with a number of different amazing artists and scientists and designers who work with biomaterials. And one of them is Fiona Bell, who unfortunately couldn't be here today because she's in Japan. And she has been doing a lot of really amazing, Fiona's work. Yeah, so she's been doing a lot of amazing 3D printed biomaterials and other types of bioplastics. This is a SCOBY vest that she created. Many recipes. Look for her recipe books, which are really incredible. She's worked with bioluminescent algae and bacteria, I think. And she collaborated with me on that piece. So the glass that you see is cast 3D prints of the spectrogram shapes. And then I blew glass into, I'll show you that process. I blew glass into that form, into that mold. And then Fiona grew the algae and put the algae in. So she's gonna talk about 3 minutes here.
Hi everyone, my name is Fiona Bell. I am a postdoctoral researcher at the the University of New Mexico, working in the hand and machine lab. I am so bummed that I am not here with you all in person today, but I'm happy to give this whole virtual talk. So, a little bit more about me. My practice is incredibly interdisciplinary. I am a trained mechanical engineer and material scientist, but I got my PhD in design, where I focused on designing with the biological world. I now actually work in the computer science department at UNM, where my focus is on the intersection of digital technologies and biological materials. So you can imagine growing biodegradable sensors from microbial cellulose, 3D printing with new locally available waste streams like eggshells or sawdust, and developing digitally enhanced bioreactors, which you can see today in the space. As most of my work happens within a lab and is mostly disseminated through academic research papers, I am so grateful to show my work with you all at the San Jose Art Institute. I am especially grateful to my collaborator, Andrea, who worked with me to create the 2 living bioreactors in this space. So, these bioreactors contain living spirulina, which is a type of cyanobacteria. Cyanobacteria were one of the first forms of life on Earth to evolve to photosynthesize. Accordingly, they played a crucial role in the evolution of life and the development of Earth's atmosphere by capturing CO2 and releasing oxygen. You can essentially think of cyanobacteria as liquid microscopic trees. However, they're much more efficient than trees in terms of capturing CO2, filtering our air, as well as filtering our aquatic environments from things like heavy metals. The cyanobacteria in this space are contained in blown glass vessels created by Andrea, who I'm sure will talk more about her process in the creation of them. The vessels are fitted with an oxygenator and an LED to facilitate ideal growing conditions for the cyanobacteria. I personally find the juxtaposition of the living organism with the traditional laboratory and digital equipment to encourage us to blur the boundaries between art and science, nature and culture, and the human and non-human. As we walk around the space today, I encourage you all to listen to the bioreactors and breathe with them as cyanobacteria feeds off of our breath and gives us air in return. Thank you all so much, and have a wonderful rest of your day.
Good, so awesome. So I won't show too much of this, but this is just another version of what you see on the video screen there of the mapping of sounds onto an animated form. And this is a little bit about the process of casting and blowing these forms. That's my teacher, Patrick Morrissey. We're blowing this huge piece. And this was at the UNM Art Museum, where we didn't have the cyanobacteria or the algae in the larger pieces, but we did have this smaller piece there, and there's my colleague Chan Choi. And I think that's my end here, but of the slides. But I do want to share also some more objects. Some more materials to touch. Some of these pieces here have mycelium grown on them, and so I've been doing some experiments with growing mycelium. So that's the kind of root structure of oyster mushroom and grown into a mold. And in fact, adding calcium to that, which is so interesting because the porosity that you get here is also coming from calcium. Calcium is making that stronger, which is really kind of cool. Maryam mentioned the 3D printed, so this is 3D printed clay, of course. That's the shape that this was intended to be, but this is a custom material, clay / glaze. I've been working with these materials that are between clay and glaze, and this material is designed to also puff up and foam. So if you compare this to the clay of that 3D printed, you can see how it's a little more foamy, and I'm enjoying how it's kind of collapsed too. But I'll also want to start to make some material. Waterproof, oh sure, yeah. They're fired. So it's clay that's been fired. But then, I've been so amazed and intrigued with Maryam's functionally graded material. I've been experimenting with my own stuff in the kiln with powdered glass and micaceous clay, because the glass is fired at about the same temperature as the micaceous clay. And Maryam and I had a brief conversation, and she was like, oh yeah, it's just in the same, you fired at the same time. I'm like, yes. So I tried it with different percentages, and what ended up happening is I actually got this like foaming of the clay itself, which I thought was not what I intended, but so interesting. Maybe I'm also wondering about the how wet it was. It may have maintained water because the glass was wet. Yeah, if I do like a preheat cycle or something like that. But I just wanted to share those kind of experiments because that's been just really fun, and I'm so thankful to be presenting with Maryam because what she does is so incredible to me, and maybe we have a few minutes for Q&A.
Sorry, I used all of your time.
I'm so into it. Yeah.
Is there a website? Do you have a website or web pages of some of the slides you showed?
Yes. If you go to ASC Lab, and UNM, you would find mine.
ASD?
ASC, like cat.
ASD Lab?
ASC, ends with C as cat.
Thank you.
And we can pass around the microphone for questions too.
Thank you so much for sharing these experiments. They're so great to touch and hold, and I'm just sort of wondering with these colorful ones, like how color became a part of the process and what you're thinking about that.
Yeah, good question. So the colors are actually glaze colors, which are often used, mason stains are often used, and also kind of minerals like calcium, copper carbonate and magnesium carbonate and stuff like that. But I think these bright colors you're seeing are more coming from mason stains, which are concrete stains, really. And I guess you also used you had some color that you were using? Okay, cool.
So they're just naturally occurring.
Mason stains, are like manufactured colors that are used to stain concrete in different colors. And often they're like, I think, like sealed, nano sealed, like, manufactured colors. They're usually proprietary. So yeah, it's interesting though, because one of the things I'm thinking, and probably I think your team is working on too, some more natural colors that might be embedded with, mycelium or other materials.
Yes, for Maryam, when you were showing the Mars residences, it mentioned the interior furnishings made from recycled plastics. I was wondering what those are made of.
Okay.
in order to travel to space, they're gonna take some plastic and they're gonna recycle it and reuse it for interior decoration. So this is the assumption that we made, and the NASA also accept that any types of plastic that we take from Earth, we could use it and repurpose it for other application on Mars. So this is the source of the plastic that it was mentioned, and it's recycled, right?
So it can be petrochemical based.
Right.
Yeah.
Anything that they took it during the mission from Earth to Mars, it will be repurposed for different application. Thank you.
This is comment question for Andrea. Yeah, it's on. It's on. Your work is really beautiful. I love the transformation from the sound to the sculpture to the animation to something that's maybe even more of a practical application. I also think it's fascinating that you were translating air quality in New York City, where air quality is quite poor, and now that you live in New Mexico and we're in a really dry air quality and high altitude, how the air is now embedded in the clay. Can you talk a little bit about like those translations and where you see your work going, and the influences of the types of contexts of air that you're capturing?
Yeah, I mean, I would say more that the context of this work is changing from these media-based visualizations and using LEDs and things like that, and that kind of technology to a more grounded or earth-based geopolymer kind of an approach. Really comes from the culture here and the slowing down and the focus that you can have of the land here that you don't really have in a place like New York City, unless you're kind of more at the water or on the river. So yeah, and just being able to connect with incredible community here of people that are working with clay and understand these materials so deeply. And just to say that as beautiful as it is here, we are certainly challenged with the mining industry and other ways in which some of these treasures that are coming from, for micaceous clay for sure, the treasures that are in our land here are really being often, challenged and changed.
This is for Andrea. So I was reading the interview with you in that book, in the field that you turned me on 2 years ago. So there was a collection of interviews with people that did field recording, which I had an interview with you. And it's like totally alien field to me, but I found it very interesting because a lot of the people that were doing soundscapes and doing ecological sounds came from some kind of performance background, like from music or whatever. And I think that you were asked about the performative aspect of your work. So I'm just kind of wondering, it's like, how did you get from there to, this more hands-on kind of thing? Is that a larger trend, or is it just your?
No, there's a lot of, at UNM and stuff, performance is really strong, yeah. And we have some wonderful people who maybe could respond to this question better than me, because you also are doing performance, but you're also making photographs, and my colleague Jessamine at Level here. Yeah, it's a good question.
I just think it's interesting that technology has gone from being something that was on the screen, right, to being something that you're shaping. I think it's like the more material things. The whole 3D printing thing is pretty different.
Yeah, I guess there's this art science. It's always like an in-depth, for me anyway, what I can take a deep dive into and try to understand. But definitely, I I think there's the movement of air creating sound, turned into creating form in this case, but in sound and other, performances that I've done. But then at the same time, like there had always been, it continues to always be this material component of air, like that particle falls is showing PM 2.5, so it's showing particles that are in the air. And so that this gives me an opportunity maybe to look more into that. I mean, there's another layer of that, which is the biological composition of air, which we all, of course, became very familiar with in COVID, and also the pollen, now with pollen, but there's even more really interesting things about the biological component of air. So I mean, for me, it feels like a continuum and not so different, but I'm gonna ask Jesse.
Well, I was just going to ask, Andrea, if you, following the same question, backing off of that, would see the sculptures, the material experimentations, like, I don't know why, but when you were presenting, I was thinking about Gordon Matta Clark and like these performances that are happening in the experimentation. And even I could apply them to the work and the competitions, like, the documentation is in the form of video, of course, because it's a practical, right, in your case. And also, the pieces themselves were destroyed, which I find just kind of really beautiful and fascinating and interesting. And so I wonder, Andrea, if you think of any of the physicality, and even especially maybe the videos, as sort of like those similar or akin to the photographs that photo collages that Gordon Matta Clark would make, or like any documentation from a performance. And then with that, I was curious if, and this is I guess for Fiona as well, but if these glass pieces, are they performances that are collaborative, that you're creating a stage? That's how I was reading them, but I just was curious if that was something that occurred to.
Yeah, thank you for that. It's really interesting, and I think like one thing I would love to do, and maybe you have access to this kind of equipment, but I would love to film inside of a kiln, and this kind of performance. Because I really feel like these are definitely documentations of some kind of action that happened. And it's always a surprise, So, and even this for sure. But George, do you have?
I wondered if there's any, like the ceiling, could that be insulation in the building? Or could it be made into some kind of roof tiles or something that would be thick or not insulated?
Maryam has probably this one. I believe there are so many research going on to see how we can adapt this material in larger scale for construction. When it comes to walls, the small amount doesn't make any sense, and there are so many research teams. One of them is in Colorado, Boulder. They are pushing all of the boundaries about large adoption of this type of material, bio-based material in real construction. So for now, everything is lab scale. I guess this is the case for you also. But the future is that we're gonna adapt it in the construction industry for sure, when we can address the commercialization and all of the up and downs to achieve the right market for that. But the goal is that we're gonna place it and use it as a construction material somehow.
One other question is, are there any?
Okay, you're not.
Are there any materials being developed that are completely, what would you call it, organic or soil and plant-based? Because the polymers, and one of the beauties of the building construction here is when it gets old, it just collapses. And then you take it and you put some water and straw and you...
Of course, we can reuse it. This is the best thing about the bio and natural material. So for cement, if we use it in concrete, then at the base moment, we cannot do anything else with that. But for this natural material, anything that has bio-inspired resources, it could return back to the nature for another application, and this is the beauty of using bio-inspired material. And there are so many good attempts going on to minimize the synthesized material like cement and adapt this type of material, which is much, much closer to the nature. And at the end life, they're gonna just return back to the nature or circle back to new application without any harm for environment.
So this is all mycelium.
Right.
Holy smokes.
Yeah, this is not to be made. No?
Okay.
Yeah, and this is actually comes from a company called Ecovative or Additive, and they are using this. They make a packing material with this. Yeah, and and really and biodegradable. But maybe Robin, you have a comment about this stuff being used in insulation and stuff? Robin's an expert in bio-based materials.
Yeah, sure. So I've done some work with the materials. My name's Rob Elkin, and I'm a graduate of UNM, and I've been presenting on natural materials and hempcrete and binder materials for a number of years, and I've done a little work with Maryam and presented to one of Andrea's classes. So yeah, there's a tremendous amount of research going on with companies like Oakham to make mycelium building materials and furniture and geopolymer materials with hemp and other materials. I used to, like on LinkedIn and other places, pull the photographs off and then to save them to put them in a presentation. But there's so many now that it's impossible to keep track of. It's basically once a week or sometimes more. There's some new company that has some new material to do all of the things in larger scale, make cement without using calcium materials with an electrolysis process, which Maryam could describe what that actually means. I'm not a material science. I've had to learn about this kind of as a layperson to understand what's going on. I'm also a planner and a construction tech, but so it's very interesting. So yes, there's a lot going on.
So this was John's question. Is if there's a biological material that's waterproof that could be used for roofing.
Yeah.
So again, in real larger scale construction, I'm not sure yet, but in the labs, there are so many work going on for adaptation of bio-based material. I believe to hit the market and have some real products still is early, because this research has been started maybe over 10 years or shorter time, and they need more time to work on adaptation and make sure they could address everything and compare it with conventional material to make sure it's, in terms of long-term durability, this is one of the problems for this material, that when they are exposed to real environmental condition, what will happen. So there are so many tests going on to make sure they are durable enough, they are resistance to heat, to so many other things, and then they will be used. To my knowledge, I guess it's not in larger scale yet, but yeah, this is what I know.
So I think that's good. So thank you very much. And